In this lecture, we're going to talk about polynomial functions. So first, let's talk about polynomials. Remember, a polynomial is a function of the form f of x equals a sub n times x to the n plus a sub n minus 1 times x to the n minus 1 plus all the way down to a sub 1 times x plus a naught, where the a values are real numbers and n is a non-negative integer. The domain of any polynomial is going to be all real numbers. Also, remember the degree of a polynomial is going to be the largest power of x that you see. So let's do a couple of examples where we examine whether or not given functions are polynomials. The first function we want to look at is f of x equals 5x squared plus 4x to the fourth. And we want to determine, is this function a polynomial? And if it is, what is its degree? So since this function matches the form on the previous slide, it has coefficients that are real numbers, and it has exponents that are integers, this is a polynomial. And remember, the degree is the highest power that you see, so we have powers of 2 and 4. Since 4 is highest, this has a degree of 4. Here's another example. h of x equals the square root of x times the square root of x minus 1. So to determine if this is a polynomial, the first thing we want to do is simplify it to get rid of the parentheses. So we'll distribute the square root of x throughout the parentheses, and that'll give us h of x equals x minus the square root of x. And we can rewrite the square root of x with a fractional exponent, so that'll be x minus x to the 1/2 power. So we want to determine, is this a polynomial? And while it might look like it might be a polynomial, remember a polynomial has powers that are integers. And 1/2 is not an integer, so this is not a polynomial. Alright, the next thing we want to talk about is identifying real zeros of a polynomial and their multiplicities. So, if f is a function, and r is a real number for which f of r is equal to 0, so when we plug r into the function we get a value of 0, then r is called a zero of f. So the following statements are going to be the same. They're going to be equivalent. First, r is a real zero of the polynomial function f. Second, r is an x-intercept of the graph of f. And third, x minus r is a factor of the polynomial f. So all three of these statements mean the same thing. So we can find the real zeros of a polynomial by factoring, and we can form a polynomial that has given characteristics by multiplying factors together. So let's look at an example where we're going to form a polynomial with given characteristics. We want to form a polynomial that has zeros -2, 2, and +3, and has a degree of 3. So if our zeros are -2, 2, and 3, then using the equivalent statements on the previous slide, we'll have factors x plus 2, x minus 2, and x minus 3. So to form the polynomial we're looking for, we'll just multiply these three factors together. So our polynomial f of x will equal x plus 2 times x minus 2 times x minus 3. We're going to break this up. We'll multiply the first two terms together using the FOIL method. So if we multiply x plus 2 times x minus 2, that'll give us x squared minus 2x plus 2x minus 4 times x minus 3. And if we simplify that, that gives us x squared minus 4 times x minus 3. And so now the last thing we want to do is again use the FOIL method to multiply these two together. So if we FOIL this out, we'll get f of x equals x cubed minus 3x squared minus 4x plus 12. Here's another example. Form a polynomial with zeros -4, 0, and 2 that has a degree of 3. Take a couple minutes and try to work this one out by yourself. When you feel like you have a good answer, go ahead and continue the lecture to follow along and see if you were right. So if the zeros are -4, 0, and 2, that means the factors will be x plus 4, x minus 0, and x minus 2. And again, we form the polynomial by multiplying our factors together. So f of x will equal x plus 4 times x minus 0 times x minus 2. If we multiply the first two factors together, that gives us x squared plus 4x times x minus 2. And if we FOIL those two together, x squared plus 4x times x minus 2, we'll get x cubed minus 2x plus 4x squared minus 8x. We combine the like terms in the middle together to give us the polynomial x cubed plus 2x squared minus 8x. Now that we've talked about the zeros of a polynomial, let's talk about the multiplicity of each zero. So, if x minus r to the m is a factor of the polynomial f, and x minus r to the m plus 1 is not a factor of f, then r is a zero of multiplicity m. So essentially what this says is if you factor things out so that you have factors raised to a degree, the multiplicity of each zero will be the corresponding degree. So let's do an example. We want to find the zeros of the following function and then state their multiplicity. Our function is f of x equals 4 times x plus 4 times x plus 3 quantity cubed. Now, typically the first thing we would want to do is factor our function out to determine the zeros, but this function is already factored for us, so we can just look at the different factors. So let's identify the zeros. The first part of our function is the number 4. Well, 4 is never equal to 0, so we can ignore that. So we look at the next part of it, the factor x plus 4. X plus 4 will equal 0 when x equals negative 4. So we have a 0 at x equals negative 4. Again, the multiplicity of the 0 is going to be the power of that factor. So since x plus 4 has a power of 1, the multiplicity of the 0 minus 4 is just going to be 1. Let's look at the next factor, x plus 3 cubed. So we can just focus in on the x plus 3. What would make x plus 3 equal to 0? That would be x equals negative 3. So our second 0 is x equals negative 3. And again, to find the multiplicity, we look at the power that's on that factor. So this has a third degree power, or power of 3. So the multiplicity of the 0 x plus 3 is going to be 3. So we can use the multiplicity at each 0 to determine how the graph behaves at the 0. For example, if r is a simple 0, meaning it has multiplicity of 1, then the graph is just going to pass directly through the x-axis at the point r0. So you see this line passes directly through the x-axis. If r is a 0 of odd multiplicity, that is, the multiplicity is 3, 5, 7, 9, so on and so forth, then the graph of the function f will pass through the x-axis, but it will be flattened at the point r, 0. So that'll look something like this. So when the multiplicity was 1, it passed directly through. When it's an odd number other than 1, it passes through, but it flattens out when it intersects the x-axis. And if r is a 0 of even multiplicity, so m is equal to 2, 4, 6, 8, so on and so forth, then the graph of f touches but doesn't cross the x-axis at the point r0. So the graph will come to the x-axis, it'll touch at that point r0, but then it'll bounce back and go back up or back down, depending on which direction it came from. So even multiplicity means the graph touches but doesn't cross. Furthermore, we can determine how a function behaves, or what function a function will behave like at the 0, r0, by plugging the value of r into the other factors. So, continuing to look at our previous example, we had f of x equals 4 times x plus 4 times x plus 3 cubed. We're going to look at the two different zeros and determine how the function behaves at those zeros. So, the first 0 that we found was x equals negative 4. And x equals negative 4 had a multiplicity of 1. So a multiplicity of 1 tells us that the graph will cross the x-axis. And we want to find out what function this behaves like at that point, x equals negative 4. So in order to do that, we're going to plug negative 4 into the other factors. So we had 4 times x plus 4. And we plug negative 4 into the other factor, so that gives us negative 4 plus 3 quantity cubed. Negative 4 plus 3 is negative 1, so we have 4 times x plus 4 times negative 1 cubed. And negative 1 cubed is just negative 1, so we have 4 times x plus 4 times negative 1. If we distribute everything, that's going to give us the function negative 4x minus 16. So at the 0, x equals negative 4, our graph behaves like the linear function negative 4x minus 16. Now let's look at the other 0. So x equals negative 3. We determined that x equals negative 3, there's a multiplicity of 3. So the graph will again cross the x-axis, but this time it will be flattened at the point negative 3, 0. To determine a function that it behaves like at this point, we're going to plug negative 3 into the other factors. 4 times negative 3 plus 4 times x plus 3 cubed gives us 4 times 1 times x plus 3 cubed. And so if we simplify that, that'll give us 4 times x plus 3 cubed. So at x equals negative 3, our graph behaves like the function 4 times x plus 3 cubed. So let's look at another example. F of x equals x minus 5 cubed times x plus 4 squared. We want to find the roots, their multiplicities, and the behavior at each. So take a few minutes and try to do this on your own. See if you can find the roots, their multiplicities, and their behavior at each, and then continue the lecture once you think you have an answer to go through the steps with me. So let's start by finding our zeros. If we look at the first factor, x minus 5 to the third power, that'll be equal to 0 when x is equal to 5. So our first 0 is x equals 5, and since the power on that factor is 3, x equals 5 will have a multiplicity of 3. Next we look at the factor x plus 4 squared. So to make x plus 4 equal to 0, x would have to be negative 4, so our other 0 is x equals negative 4. And since the power on the factor is 2, it has a multiplicity of 2. So let's consider the behavior at each 0. At x equals 5, the multiplicity was equal to 3, so that means that the graph will cross the x-axis, but it'll be flattened when it crosses. And to find a function that our function behaves like, we'll plug 5 into the x values and the other factors, which will give us x minus 5 cubed times 5 plus 4 squared, which is x minus 5 cubed times 9 squared. And if we simplify that, that'll give us 81 times x minus 5 cubed. So at the 0 x equals 5, our graph behaves like the graph of 81 times x minus 5 cubed. Now let's look at our other 0. So at x equals negative 4, the multiplicity was 2. This means the graph of the function will touch the x-axis but not cross. So to find the function it behaves like, we'll plug negative 4 into x at our other factors. So we have negative 4 minus 5 cubed times x plus 4 quantity squared, which simplifies to negative 9 cubed times x plus 4 squared, which will give us negative 729 times x plus 4 squared. So at the 0 x equals negative 4, our graph behaves like negative 729 times x plus 4 squared. Next, we'll talk about turning points for the graph. So if f is a polynomial of degree n, then f has at most n minus 1 turning points. And conversely, if the graph of a polynomial has n minus 1 turning points, then the degree of the polynomial is at least n. Last, we want to talk about the end behavior of the graph. So we can identify how the graph of a polynomial will behave at the ends, where x is very large or x is very small, by examining the leading term of the polynomial, a sub n times x to the n. So there are basically two things we want to look at with this leading term. We want to look at the sign of the leading coefficient, because that indicates the direction of the right-hand or positive side of the graph. If the coefficient is positive, that means the graph will go upward on the right-hand side. If the coefficient is negative, that means the graph will go downward on the right-hand side. So first look at the sign and use that to determine what happens on the right-hand side of the graph. Then look at the degree of the polynomial, and that will indicate the direction of the left-hand side in relation to the right-hand side. So basically this means that we'll look at what happened on the right and then use the degree to determine what happens on the left. If the degree is odd, then that means that the ends go in opposite directions. So if the right-hand side goes up, your left-hand side will go down. And if it's even, then if the degree is even, that means that both ends go in the same direction. So if the right-hand side goes up, the left-hand side will go up as well. So let's just look at that a little bit further. Basically, there are 4 possibilities when you look at the leading term. The first possibility is that the coefficient is positive, so that means the right-hand side goes up, and that the degree is an odd integer, which means that the left-hand side will go down. The second possibility is that the coefficient is negative, means that the right-hand side goes downward, and that the degree is odd, which means that the left-hand side will do the opposite, it will go upward. The third possibility is that the coefficient is positive, so the right-hand side goes up, and that the degree is even, which means that the left-hand side will go up also. And finally, we have the sign of the coefficient is negative, which means that the right-hand side goes down. And the degree is even, which means that the left-hand side goes down as well. So let's continue our example and put everything together to sketch our graph. So we had f of x equals 4 times x plus 4 times x plus 3. Let's start by looking at the end behavior. If we were to multiply the factors together, just looking at the first terms, we would have 4 times x cubed, which would give us 4x to the fourth. So our leading coefficient is 4x to the fourth. The coefficient is positive, which means that the right-hand side goes up, and the degree is even, which means that the left-hand side will go up also. So we can see that our end behavior is going to be up, up. Next, let's look at the zeros, or the local behavior. Previously in our example, we figured out the zeros are going to be x equals negative 4 and x equals negative 3. So we'll go ahead and draw those on our graph. So we plot the point negative 4, 0 and negative 3, 0. Those will be the x-intercepts for the function. For the 0, x equals negative 4, we know there's a multiplicity of 1, which means that the graph will just pass directly through the 0. And since we know that the left end behavior goes up, we can draw a line that starts upward and comes down and crosses at the point negative 4. For the 0, x equals negative 3, we have a multiplicity of 3, which means that the graph will cross the x-axis, but it'll be flattened. And so if we draw that in, crossing at negative 3 but being flattened, and continuing upward, we'll see that the right-hand side goes up, which matches our end behavior. So this is a very general sketch of what the graph would look like. If you want to determine how far down the graph goes, or get a little bit more accuracy, you should plug in additional points into the function and make sure that your graph passes through those points. But this is just a rough sketch. So let's do one final example where we're going to start with a function and we're going to do all kinds of analysis on it so that we can sketch the graph. So we have the polynomial function f of x equals x times x plus 2 squared. We first want to find the x and y intercepts. Then we want to determine does the graph cross or touch at each x-intercept. Next, we'll determine the end behavior of the graph and the maximum number of turning points. We'll determine the behavior near each x-intercept, and then we'll put all of the information together to sketch the graph. So let's look at the function f of x equals x times x plus 2 squared. We'll start by finding the intercepts. Remember, to find the x-intercepts, you set y, or f of x, equal to 0 and solve. So we have 0 equals x times x plus 2 squared. Using the zero product property, we can split the two factors up, so either 0 equals x or 0 equals x plus 2 squared. And if we solve both of those, we get 0 equals x or x equals negative 2. So our x-intercepts occur at 0 and negative 2. And to find the y-intercept, we plug 0 in for x. So we get f of 0 equals 0 times 0 plus 2 squared, which if we simplify just gives us 0. So our y-intercept is going to be 0, 0. Next, we want to determine whether the graph crosses or touches at each intercept, or at each 0. So when x is equal to 0, we have a multiplicity of 1. And a multiplicity of 1 means that the graph will cross completely. So at x equals 0, the graph crosses. At x equals negative 2, we have a multiplicity of 2. And 2 is even, so that means at x equals negative 2, the graph will touch the x-axis, but not cross. Next, we want to evaluate the end behavior. So again, if we were to multiply this function out, we would get a leading coefficient of x cubed. The sign on x cubed is positive. That means the right-hand side will go up. And the degree is odd, which means the left-hand side would do the opposite. So our end behavior will be down, up. Next, we want to determine the maximum number of turning points that our graph could have. So since the degree of our polynomial is 3, that means the maximum turning points will be 2, one less than the degree. Next, we want to evaluate the local behavior at each 0. So at x equals 0, to determine the local behavior, we'll plug 0 into the other factor. And so that'll give us x times 0 plus 2 quantity squared, which simplifies to 4x. So at x equals 0, our graph behaves like the line 4x. At the 0, x equals -2. To find out its local behavior, we'll plug -2 into the factors other than x plus 2 squared, which gives us -2 times x plus 2 squared, and we'll just leave it like that. So at -2, our graph behaves like the quadratic -2 times x plus 2 squared. Finally, we want to sketch the graph of this function. We'll start by marking our x-intercepts. So we have an x-intercept at -2 and at 0. So we know that our graph will touch the x-axis or cross the x-axis at those 2 points. So going from our end behavior, we know that the left-hand side should come from point downward. So we'll start down there and come up to -2. And at -2 the graph touches, so we'll come up to -2, touch, and go back down, looking something like this. Now, we know at x equals 0, the graph crosses, so we're going to need to go back upward to cross through at x equals 0. And the end behavior on the right-hand side goes upward, so we'll just keep going up, which will look something like this. Now, remember, this is just a rough sketch. If we want a more accurate graph, we should pick some points in between our zeros and on either side of the 0 to plug in to make sure that things match up. But this is a sketch of what our graph should look like.